Hi, and welcome to Failurology, a podcast about engineering failures. I'm your host, Nicole, and I'm from Calgary, Alberta. We're in that weird in-between time. The craziness of Christmas is over, but it's not quite New Year's. Most people are still off work, things are quiet, everyone is relaxing, and probably a little too full from all the food they ate. Although, maybe that's just me. I haven't really left the house to confirm one way or another. I personally have been reflecting on what I've accomplished in 2020 and what I hope to accomplish in 2021. I realized recently that I tend to carry around some anxiety about not doing enough, like my stressful 9 to 5 is insufficient. While I think that's irrational and that overall anxiety helps push me to pursue my dreams, it was still something that was nagging at me. But what I realized was that this podcast has helped in a huge way. As scary as making it has been, I've learned so much from recording to editing to marketing. So thank you for joining me on this journey so far. And also, pursue your dreams. Don't let fear or anxiety hold you back. Get out there and get it done. This week's engineering failure is the Hartford Arena roof collapse, which is the first known engineering failure caused by a computer-aided design. Now, my discipline is mechanical. Structural is not in my wheelhouse. I can read the drawings to find beams and slab thickness, but I really had to dig deep to research this one, and I learned a lot. I think this is a really important failure due to being the first computer-aided design to fail. But before I get into all of that, the news. This week in engineering news, the 11.2 kilometer Estroy tunnel in the Faroe Islands contains the world's first subsea roundabout. The Faroe Islands are an autonomous territory within the Kingdom of Denmark, located 320 kilometers northwest of Scotland, halfway between Norway and Iceland. The islands are roughly 1,400 square kilometers with a population of just over 52,000. The tunnel opened on December 19th of this year and connects the Streymoy Island, where the capital city of Tórshavn is located, to two parts of the Estroy Island. The tunnel travels from Streymoy across the bay and then wides at the roundabout to serve two arms of the Estroy Island. There is a bridge further north that connects these two islands, but the tunnel reduces travel time by up to an hour and a half. This will allow services to be more available than before, as well as significantly reduces commutes for residents. Construction of the tunnel began in January 2017. The tunnel is 187 meters below sea level at its deepest point, with the steepest grade no more than 5%. It's estimated that the tunnel will see 6,000 vehicles per day. Costs for the tunnel will be repaid through toll fees. I do love a good tunnel. I've run the Detroit Marathon a couple of times, and the route runs through the Windsor-Detroit Tunnel, which is my favorite part of the race. And I think I'll have to add Faroe Islands to my list of places I want to travel to. This tunnel sounds really cool. If you want to read more on the tunnel, check out the website page, link in show notes for this episode. The article also contains a really informative video on the tunnel. Now on to this week's engineering failure, the Hartford Arena roof collapse in 1978. The first known engineering failure caused by a computer-aided design. Going into research for this failure, I had expected that the failure would have gone somewhat unrecognized by all parties until the collapse occurred. But as it turns out, several people pointed out excessive deflection throughout construction, and it went ignored. The arrogance that the new fancy computer model couldn't be wrong really did the engineer in here. As budgets and deadlines tighten, we all rely more and more on technology to help us. But we have to double check the calculations. Also, when the contractor tells you there's a problem, you should at least hear him out. And always double check your numbers. Unfortunately, the legal outcome of this failure has not been made public, so information was a bit limited. But I was able to dig up enough to tell you about the cause and, of course, what we can learn to prevent future failures like this from happening. Construction on the Hartford Arena started on April 2, 1971, and the arena opened on January 9, 1975. The arena cost $30 million, which is equivalent to about $143 million today. The arena is owned by the city of Hartford. It has over 10,000 seats and was built to house the Hartford Whalers, who were part of the World Hockey Association from 1972 to 1979, and later in the NHL from 79 to 97. The Whalers started out in New England, moved to Hartford, Connecticut in 1974, and then moved to Carolina in 97 to become the Carolina Hurricanes. The architect on the arena was Vincent Kling, and Fraioli, Bloom, and Yesselman engineers, also known as FB&Y, were the structural engineers of record. At 4:25 a.m. on January 18, 1978, following heavy snowfall caused by Winter Storm Igor, the roof collapsed. Over 5,000 people had been in the building 5 to 6 hours earlier for a basketball game, but luckily no one was in the building when it collapsed. Finally, a failure where no one was hurt. Computers were relatively uncommon in the 70s. I'm not saying they didn't exist, but it's not like everyone had one in their house. I think we got our first computer in 1993. Good old DOS and floppy disks. The engineers used computer analysis for the structural design calculations. Even though the design was susceptible to buckling, the engineers were overconfident in the computer's ability, which led to them ignoring evidence of a problem. The design was a typical space frame design, which is a rigid, lightweight, truss-like structure constructed in an interlocking geometric pattern, specifically triangles, typically built from steel tube or eye struts, which is a really fancy way to say that the roof is supported by upside-down pyramids made from steel truss-like members laid out in a grid pattern. Space frame design allows for lighter but stronger structures. It's common in industrial buildings, warehouses, swimming pools, airports, and stadiums, like the Rogers Center where the Blue Jays play. Wherever a large open space is required with minimal columns. Maybe you, like me, have seen the structure style hundreds of times and just never knew it was called a space frame design. The one at the arena, however, was not implemented correctly. The arena's roof truss structure was 3 meters deep, 91 by 110 meters in plan, 25 meters above the floor. In a space frame design, it's important that all of the intersecting truss members meet at the same points so the load is transferred evenly. This is somewhat challenging to explain, so please be sure to look at the photos on the episode webpage for more info. But let's say you have your upside-down wireframe pyramid in a typical space frame design. We have a big square at the top made of 4 structural members, a little square in the middle, and a point at the bottom, and a bunch of other structural members connecting them all together. The points from several upside-down pyramids are then connected together using additional structural members to form a cohesive roof system. It's imperative that each of the intersecting structural members meet at the same spot, whether that be at corners or at the middle of spans. But that didn't happen on the Hartford Arena. The top chords intersected at different points than diagonal members, which resulted in an increased risk of buckling. In addition to this major problem, there were 4 other issues that contributed to the failure. The structural members were cross-shaped, which had a lower resistance to buckling than square or round tube or eye-shaped members. We'll get into the failure investigation shortly, but I wanted to mention that the use of cross-shaped members was based on the design assumption that bending and torsion would be negligible in the space truss. The top chord didn't directly support the roof panels. Small posts were installed between the top square corners and midpoints and the roof panel. This was done to allow sloping, meant to eliminate bending stress. There were only 4 columns to support the entire roof structure, and they were located 13.7 meters inside the roof edges to support the entire roof. And lastly, the frame was not cambered or curved, which increases strength of members. If you didn't quite follow all of that, it's okay. The important part to know is that the roof was underdesigned and not constructed properly. Construction was divided into 5 contracts, managed by a construction manager. The setup isn't uncommon, but unless you have a construction manager who's on the ball, it's easy for things to slip through the cracks, creating confusion over who's responsible. In addition to gaps in construction, there were also gaps in the design and inspections. The architect recommended that a structural engineer oversee construction of the steel. This is very common. I've seen third-party steel inspections carried out on a lot of projects, but the construction manager refused and said he would do it himself to save money. That said, the design engineer should have done some inspections of their own, even a general overview. Interestingly enough, following the collapse, the construction manager tried to dodge all responsibility after the collapse, claiming design error. Peer reviews were commonly required in Hartford for projects of this magnitude, with new design techniques, but not for this project. Connecticut is one of the few states that requires peer reviews today. I've seen clients hire other consultants for peer reviews on various designs over the years. Sometimes they just want a second opinion on a critical system, but I can't recall a time when the authority having jurisdiction, or the city, required a third-party review, although I may not have been involved. Throughout the process, engineers assured the city that the deflection was acceptable. Engineers were negligent for not checking design and again for ignoring deflection. During construction, deflection was noted when the interlocking pyramids were constructed on the ground. On the ground! You've got to be kidding me. I personally would have not lifted them into place at this point, and I probably would have called in a favor or two for an off-the-record second opinion on the structural design, just to see what I was dealing with exactly. When they hoisted the roof into place before the roof panels were installed, the trusses experienced twice as much deflection as originally calculated. The deflection was so bad that the windows didn't fit. Ironworkers reported deformations were unreasonably large. Some accounts suggest they vowed never to enter the building once it was complete. Even a citizen expressed concerns. This would have been another great place to stop and ask some questions instead of plowing ahead. Look, I get it. There are deadlines and budgets and expectations, but I'd like to think that the expectation the roof stays up should really outweigh the others. And for what it's worth, it took 2 years to rebuild the roof and reopen the arena after the collapse. So when you factor that into the equation, a couple weeks to check the design that's already showing signs of extra stress isn't really that long. Now, as I said, there was a formal investigation into the collapse. Lev Zetlin Associates Inc. was hired, and here is their laundry list of findings. The structure started failing as soon as it was completed. The design underestimated both the live and dead loads by about 20%. The dead load is the static load, or the weight of the structure itself, and the live load is also known as the dynamic or variable loads, which in this case was the snow from Winter Storm Igor. Some members were overloaded by 852%. 852%. It's a big number. The structural details omitted midpoint braces for the exterior rods of the top layers, and the interior rods were partially or improperly braced at the midpoint. This goes back to my previous comment about the structural members intersecting at the same point. The slenderness ratio of members violated the American Institute of Steel Construction Code provisions, and members with bolt holes exceeding 85% of total area also violated this code. Some steel didn't meet spec. The computer model only included the main members for the structure. If it had included intermediate members, the instabilities and primary bending moments would have been detected. The ultimate cause of the failure was the top layer, which buckled, causing other layers to buckle. The lower layer, originally in tension, was now in compression and also buckled, causing the entire roof to collapse. Computers can run calculations very fast, much faster than humans, and it allows them to be run at minimum loads to provide a more economical design. But this limits the safety factor, which limits room for error in calculations, manufacturing, and installation. Should safety factors be increased for high occupancy structures? And who is ultimately liable for faulty designs where software is used? In Canada, the engineer is liable. There's a disclaimer from the software manufacturers which shifts liability to the user, and provincial engineering associations agree on this. In this particular case, there's a simple equation to compare computer-generated stress called the Euler buckling equation. It would have taken minutes to double-check. 6 years after the collapse, an out-of-court settlement was reached. This did not allow for legal precedent to be set for future cases, and the outcome of the settlement was not published. The arena reopened after the collapse on January 17, 1980, 2 years less a day after the collapse. So what are the takeaways from this failure? What are the lessons learned? It's important to outline and quantify responsibility in contract documents. Double-check computer calculations. Even if you use previous project, rules of thumb, or simple calculations, it's best to double-check the computer calculations when everything is still on paper before it's built. When someone says there's a problem with the design, hear them out and double-check the numbers. Review the installation of your designs during construction. This is important. Read literature related to your profession to stay relevant. Engineering failures are an integral part of engineering. Engineers must educate themselves on failures from peers before them in order to prevent history from repeating itself. This is the main objective of this podcast, to educate engineers on past failures and prevent future ones from happening. I hope you found this failure as interesting as I did. I'm starting to see a theme that engineers are told there's a problem and just ignore it until it's too late. So please don't be one of those engineers. Check out the podcast page, link in show notes, for photos from this week's episode. And if you want to chat with me, my Twitter handle is @failurology, or you can email me at thefailurologypodcast@gmail.com. Thanks everyone for listening, and tune in next week to hear about the Malahide Viaduct, a collapse that stopped the only train route between Dublin and Belfast for 3 months in 2009. But more on that next week. Bye everyone. Talk to you next year.